Good afternoon, everyone. Okay, so we will continue with our lecture under Unit 1, Systems Thinking. Okay, so this is going to be lectures 1-2 to 1-4, as we have on the course guide. I hope you were able to read through the relevant chapters, especially on VANIC. All right, so as I mentioned, we're going to discuss lectures 1-2 to 1-4 today. Sige, so let's start with the quantitative tools or qualitative tools, system tools for energy system analysis. Okay, and as you've probably read from VANIC, some of the qualitative tools that were discussed are stories and causal loop diagram. No, and we also have in chapter 2.5, I think. They also discussed about the Kaya equation or the Kaya identity. So we're going to talk about those. Okay, and then under quantitative tools, you're going to have projecting rate of growth or penetration of energy technologies. And under that, you have your exponential function, your logistic function, and your triangular function. And then the chapter also discusses about estimating future situation of energy-related measures such as consumption and pollution. Okay, so under this, you have scenario analysis and quantitative modeling. And then tools for determining whether a particular technology is acceptable or when you are choosing the best alternative solution. So under here, you have your life cycle analysis, you have energy return on investment, you have multi-criteria analysis and optimization. And then, of course, under quantitative tool, you also have understanding contribution of underlying factors such as regression analysis and division analysis. Okay. But before we talk about these things, let's first discuss the general system goals, okay, the categories of general system goals, okay, and you have physical, financial, and environmental. So under physical, you might want to provide solutions to your energy system such that your energy system is efficient, such that it is reliable, and such that it is safe. Okay, so these are physical goals. And then, of course, you have financial goals. If you're an individual or you're a household, your goal might be to reduce expenditures. Okay? In the case of a commercial establishment, it might be to maximize return on investments. Okay? And of course, you have your environmental goals that are in tune with sustainable development goals. Okay, and in response to these goals, you have 4 general categories of energy solution options. So you can see them on the screen, but I know that you've also read about them. So you have conserving through personal choice. And then you have conserving by replacing end-use technology, conserving by replacing energy conversion technology, and then replacing existing energy sources with alternatives. Okay, so what are the differences? In the first one is mainly behavioral, no? It's the individual's choice, okay, to identify technologies that can help him or her reduce his or her energy footprint. And then, of course, the second one is replacing the technology that is making use or contributing to the demand of energy. In the third one, you're still using the same conversion technology, but you might switch to something that is more efficient. And then the fourth one is completely switching to another type of fuel. Okay, good. Sige, let's move on to the next slide. So, and all this talk now, eco-efficiency, they actually contribute to the idea of sustainable development. And we talked about the definition last time. And under sustainable development, these are the most significant goals, no? Protecting the environment, achieving equity, and achieving intertemporality. Ano bang ibig sabihin ng intertemporality? Sige, so under sustainable development, and you've probably seen this in other courses or in seminars that you've attended, or you just see it everywhere now because sustainable development has become a buzzword. Okay, you've heard that there are 3 dimensions to it. You have the environmental, you have the economic, and then you have your socio-cultural dimensions. Okay, and these are usually referred to as the triple bottom line. Bakit dati ba? Anong nangyayari? Kaya siguro nakikita din natin ngayon, we can see in companies, merong tinatawag na CSR, Corporate Social Responsibility. This is actually related to the desire for companies to contribute to sustainable development. Or it could be desired by them or they are pressured to join in this effort. Okay. Okay. As you can see on the slide here, okay, we have 4, let me just switch to that. We have 4 squares here, no? Okay, you have energy disruption, water disruption, biodiversity disruption, and food supply disruption. Bakit ito pinakita ni Vanek? Why was this shown? And as you can see, the title of the slide is Expanded View of the Implications of Energy Systems. Okay, because again, as we mentioned before in the previous discussions under the introduction to systems thinking, systems can be subsystems of bigger systems. And we basically want to show here that energy systems are part of the bigger societal system. Okay, and the systems of our societies can affect subsystems such as the water system, biodiversity, as well as food supply, no? And any disruption in each of these subsystems can actually affect the others. All right, so let's look at energy disruption. This could include excess CO2 emissions, detrimental changes to climate patterns. Okay, under water disruption, you have floods and other natural disasters, droughts, stress on potable water supply. And then you have biodiversity, loss of habitat, accelerated population decline and extinction, movement of invasive species to new areas. And under food supply, you have reduction in crop yields and disruption to crops. O paano ba nakakaapekto yung energy systems sa food supply, water disruption as specified here, no? As well as biodiversity? Could you think of a particular example? Now we're going to slowly move on to the tools, no? But I'd just like to point out that in systems approach, okay, it's usually top-down. Okay, so systems view is a top-down approach rather than a bottom-up approach. We recognize the hierarchy of systems, okay, and of course, the hierarchy of systems starts from the purpose of the system. Okay, all the relevant functional relationships are analyzed from the top-down. And this is from Lankard and Fabriki. Components and attributes are important, but only to the end that the purpose of the whole system is achieved through the functional relationships linking them. Again, we go back to the 3 components of a system, which are, dapat alam niyo yan. Sige. Okay, so we talked about that already. Now, how do we actually implement systems approach? Actually, the way that Vanek and colleagues discussed system approach is a little bit vague. Okay, we will make it a little bit clearer later on when we go on to decision analysis. Okay, because actually decision analysis is a tool for systems approach as well. Okay, but some important questions that you will have to ask are the following. 1, how is the boundary, components, and purpose of a system determined? Now, is it preordained? Preordained ba to? No, as you know, hindi, diba? Okay, you can actually change the system boundary, no? Depending on how you frame the problem okay, and what the purpose of your analysis is. And then, should systems be purely physical? And again, you know that this is not true. Okay, meron kayong mga institutional components, you have your informational components as well. And then, how do we know that we have reached the right abstraction of a system? Again, as I mentioned last time, no model is correct. Every model is wrong. It's just a matter of how accurate the model is in terms of abstracting the system. Okay, so we can never probably reach the right abstraction of a system. Maybe there are better abstractions of a system, so to speak. Okay, so as I mentioned, there are 4 steps, no, to implementing the systems approach, as Vanek and his colleagues discussed in the book. And these are determining the stakeholders, determining the goals, determining the scope and boundaries, and iterating and revising plans as project unfolds. Okay, so you will see that the first 3, okay, are going to be common steps in decision analysis. And the 4th one is, as I mentioned, it's vague. And we will discuss that further. We will elaborate on that further as we go on to the next unit. Okay, but now we first discuss the qualitative and quantitative tools in systems analysis. Okay, so here the book first discusses the difference between stories, scenarios, and models. Okay, and stories are basically a qualitative tool, okay, to describe the cause and effect relationships in a certain system, a certain problem. Okay, while scenarios and models are actually the quantitative tools. No, scenarios are projection, okay, quantitative projection between the connection between the inputs and outputs. And in this tool, there is no need to prove that values are best fit for the current or future situation. So here, imagination is important. Of course, imagination that is informed by your expert knowledge in the topic. No, so dito you think about what if something happens, what would happen to the energy system. Okay. And then you have models. So models, as you know, okay, are quantitative way of predicting future outcomes. And in terms of predictive power as well as data requirements, this increase from story to model, obviously, no? However, we mention here stories because they are very important in terms of helping you contextualize the problem and providing background as to why the problem in the first place is important. Okay, and it also provides some insight on how you can tackle the problem. So here we will go through 3 examples lang, no? And by the way, as you've probably heard before, stories are very powerful tools because they tap on our imagination, okay, and they provide a more coherent picture, okay, of what we are, what problem we are facing. So in the examples that were mentioned in Vanek et al., they give titles to the different stories, no? And these titles help us visualize, okay, visualize and understand better in our minds because we make use of metaphors, okay, to better have to have a better grasp of the problem. So for example, a rising tide lifts all boats. Okay, so you can see the picture here. So the rising tide lifts all boats. Ano ba yung rising tide na tinutukoy dito sa story na to? So let's just go through the story, no? Improvements in the national or global economy will improve the situation for all people. So that is the argument. And also make possible investments in environmental protection, including cleaner energy systems. So if there is enough momentum for, you know, some of the big countries to improve, okay, their investments in terms of protecting the environment, okay, then this might have a ripple effect to other countries as well and help them increase also their performance in terms of protecting the environment, basically. Okay. And then you also have a story, okay, which was entitled The Tipping Point. Okay, The Tipping Point. Here, basically, the story tries to explain, okay, the case that the world is facing right now in terms of climate change. No, there is a tipping point as to the amount of anthropogenic greenhouse gas emissions. Okay, that can cause irreversible damage to our environmental system. So tipping point, dali maintindihan. And then the airplane making an emergency landing. So ang story dito is if the pilot, okay, doesn't decide quickly, okay, then there is of course a greater chance that nobody will be safe. Okay. However, if the pilot decides too quickly, okay, too quickly, no, too abrupt, the decision might not be a good one, which can result into a crash landing maybe. Or if the pilot decides too long naman, okay, the plane might run out of fuel, for example. So this could be likened in an energy system when for example, the government, for example, decides to make draconian measures, okay, to save its energy system. The measures might too drastic in such a way that it can cause an upheaval in the society. So, for example, in Europe, no, there is one country that suddenly decided to close down all its nuclear power plants, no? And this caused an upheaval in some sectors of the society, especially those who are working in that sector. Okay, or when you close down all coal power plants, no, there are going to be sectors of the society that will be affected. No? So these drastic measures, no, that are intended to occur in very short periods of time, okay, might have a negative impact also on the other dimensions and stakeholders of the society. In the meantime, on the other hand, if you don't make quick decisions, okay, within the allotted period of time, okay, baka naman it's too late na to invest. Or in the context, for example, of climate change, if you wait too long to, say, transition to cleaner energy resources, then it might be too late. Okay, we might not be able to meet your reduction target so that we can prevent the irreversible damage to the environment. Okay. And then we have what we call the currency model of energy conversion. So you can see here your energy resource, and then you have your currency, and then you have your service. Okay, so for example, here your energy resource could be coal mine, and then your conversion technology could be a power plant. Your currency is the electric transmission line through which electricity goes through. Your service technology is a washing machine. And then you have your service, which is clean clothes. Okay, so it just helps you go through you're trying to go through the life cycle, and you're trying to understand what enables you to sort of purchase a service. Okay, and of course, as you know, and this is linear, by the way, so you can't really see. One of the disadvantages is you can't really see dynamics, okay, in the system, and of course it doesn't show any change through time, no. But the beauty of this is that it can also give you an idea that there could be other currencies. Okay, there could be other currencies to provide the service that is needed in the system. So for the other examples of energy currency models, you have them here. They are shown also in VANEC. So we already discussed the first one, and then you have for transportation, the second and the third one pertain to transportation. And here in the second and third example, you can see that the upstream components could be different. Okay, so these pertain to the different energy options that you might have to provide the same service. Okay. So now we transition to, okay, we will transition later on to quantitative now, but before we go to that, let's first discuss causal loop diagrams, which should be familiar to you since you already did your Pecha Kucha. Okay. Before we go to that, let me just mention, these are some of the common system dynamics models. So you have models on exponential growth, which we will discuss later, saturation, as well as causal loops. And now we're discussing causal loops. All right, so let's move on to causal loop diagrams. So as you know, these are maps, basically, of the connections between components which interact in the system, and where each component is characterized by some quantifiable value. But of course, as you know, we don't show the quantities in the diagram. It's basically a qualitative way of looking at the entire system with just one graph. Okay, so in the succeeding slides, no, I will actually want you to work in groups. Okay. And then I will call on members of the groups, 3 groups later on to discuss the diagrams. Okay, so we have causal loop diagram 1, 2, and 3. So they are figures 2-11, 2-12, and 2-13 in the book. And it's very neat, right? In just half a page, you can say a lot about the very complex interactions of the energy system at the macroeconomic perspective, right? Oh, you're gonna probably need several pages to explain that in words. So that's the beauty of feedback loops. Okay, so I hope you appreciate it. And maybe I will see some feedback loops in your projects later on. Okay, sige. So let's move on to the next activity. Okay, so suppose your group is tasked to recommend a sustainable energy system in support of study or work from home. Generate a preliminary system analysis using qualitative system analysis tools. In particular, present the following. So quick discussion lang, no? Quick brainstorming. Okay, so you have your context of your analysis, a story, and then system boundary, and then your causal loop diagram. In the context of working from home, right? It's a different environment now. And of course, you need energy systems to support you in performing work from home or study from home. Okay, so it doesn't have to be very complex, your analysis. So think computers, you know, electricity that you need for that, what happens to your residential electricity consumption. Okay, I'm leading you towards a particular problem now, but something like that. Okay, and how can you make that more sustainable? You create your own story. Actually, I devised this problem given our situation right now, the global situation right now, which pushed us to the setup of study or work from home. Okay, and of course you can, well, you might be able to show it in your causal loop diagram later on, what happens to the energy system, okay, because of the work from home or study from home setup. Sige, you can discuss with your group mates more. Okay, sige. So we've already talked about causal loop diagrams. Let's move on to the quantitative tools. The first 3, these are basically distribution functions, no? But they are mostly used for estimating penetration or growth of technology into the market. Okay, because it has been observed that in most cases, these are the behavior of technologies in the market. So we have the exponential growth. Okay, E of T here is the annual energy consumption in year T, while A and B are parameters that fit the growth to a historic data trend. So there's a data set in Vanek et al. Okay. And I didn't include it in the presentation anymore because this is a very familiar equation to you anyway. So just review that. Okay. So the exponential equation was basically used to predict the annual energy consumption for succeeding years. Okay. I think this was the graph that was used in that example. Okay, but another idea that usually appears in system dynamics is asymptotic growth. Okay, at some point, a technology reaches a point where it does not really grow anymore in terms of its penetration of the market, or maybe energy consumption, as you might have seen in your homework if you've already started it. Okay, in terms of the energy consumption of a country. Okay, at some point, nagle-level off yung demand ng country. Okay, maybe at an individual level or at the country level. Okay. The other two important functions include the logistic curve and the triangular function, which are exhibited in most behaviors of technologies. So they include both the accelerating growth near the beginning, okay, of the model lifetime, and the slowing growth as the limits are approached near the end, as you can see here. Okay, so you have here your logistic function in terms of penetration of technology into the market. F of t is equal to the fraction of the population that is converted to use the new technology at time t. And then big F is the maximum fraction that is expected. And then C1 and C2 are the parameters of the function. Okay, so you can use this to predict, as we will see later on in the example. And then you also have your triangular function. Okay, there are two cases. If A is less than or equal to T, if T is greater than or equal to A, or if it's less than or equal to A plus B over 2, then you use the first equation. Otherwise, you use the second. Okay, and F of T is just the percentage relative to completion of growth. And then A is the start time and B is the end time. So let's take the example 2-2 from Vanek. So this is the example. Automobile production in a fictitious country amounts to 1 million vehicles per year, which does not change over time. Starting in the year 1980, automobiles begin to incorporate fuel injection instead of carburetors in order to reduce energy consumption. The task is to compute for future penetration of fuel injection as follows. So using the logistics function, suppose we treat 1980 as year 0 and that 5,000 vehicles are produced with fuel injection in this year. Now in 1981, the number rises to 20,000 vehicles. The expected outcome is 100% saturation of the production of vehicles with fuel injection. Now, the problem is how many vehicles are produced with fuel injection in 1983, given this. Okay, and the solution is also shown in the book. Okay, so T here, since we're starting from 1980, T is equal to 0. Okay, given the equation F of 0. And we are given two unknowns, two equations, okay? So we use the first one where T is equal to 0. Okay, we can compute for C1, where C1 is equal to, where F of 0, okay, is 0.5%. Okay, saan galing yung 0.5? That was the penetration at year 0, yung 5,000, no? And now, given this, we can solve for C1, and C1 will be equal to negative 5.29. Okay. Next, in 1981, okay, that will now be time equals 1, T equals 1. Okay, we have the given was that there will be 20,000 vehicles in the fleet. So that's 20,000 over 1 million. Okay, that's 2%. Okay, so now we can solve for C2. Okay, so T here is equal to 1. We know what C2 is. Okay, and we know that F of 1 is 2%. So C2 will now be equal to 1.4. Okay, and then lastly, we solve for what is asked in the problem, which is the penetration at T equals 3, 1983. Okay, we use the two parameters C1 and C2. Okay, and use the exponential equation to get the penetration at year 3 F of 3, which is equal to 25.2%. Okay, so that means 0.252 of 1 million, which is equal to 252,000 cars, is estimated to be made with fuel injection in 1983. Okay. Next, using the triangle function. Suppose that only the total time required for a full transition to fuel injection is known, and that this transition will be fully achieved in the year 1990. Okay, how many vehicles are produced with fuel injection in 1983 according to the triangle model? Okay, so una muna, we see that A plus B over 2, okay, is greater than T, which is equal to 3 kasi 1983 yung hinahanap natin. So we use the first equation. Okay? And based on the first equation, ginamit lang niya P of T dito instead of F of T. Okay? Based on this equation, you have 2 times T, which is 3 in this case, minus A. Ano yung A natin? A is 0, the start time. And then B is 10 because the end time for the full penetration is 1990, right? So 10, okay? And using the equation, it gives you P of 3 or F of 3 is equal to 0.18, okay? We multiply that by 1 million, we have 180,000 cars built with fuel injection in 1983, okay? Sige, so these are two useful equations that you can use to estimate technology integration. Okay, just a note, given the two behaviors of the curves, you will notice that up to this point siguro medyo pareho pa sila, but there's a big disparity with respect to the estimates kasi at 1985 your triangular results would be at 50% penetration, while your logistic will already be at 85%. So as in any model, there will probably be validation required for this. Okay, for example, in your research, you're trying to investigate which one is better than the other, okay, or a way to verify which one is better than the other. Okay, sige. So now we move on to another quantitative tool, which is the Kaya equation, or sometimes known as the Kaya identity. This was developed by Yoichi Kaya from the University of Tokyo. It basically states, okay, this equation states that estimation of CO2 emissions of a country is influenced by 4 parameters. And what are these 4 parameters? You have your population, you have how rich the population is, okay, GDP over P, okay, how much or what is the rate of energy consumption, okay, with respect to your wealth, and then what is the rate of CO2 emission per energy unit consumed. Okay? Sige. So there was a discussion with respect to the benefits as well as the cons of this framework, no? Because this equation can be actually translated into a framework. It basically says, as a framework, you can control the emissions of a country by trying to control any of these parameters, okay? On one hand, there are some things that are lost, okay, from this equation. And what are these? Ano yung isa sa mga differences in terms of, okay, I will lead you na. energy consumption ng industrialized and industrializing countries. Okay, so that will be made more concrete by looking at the numbers here. I'm not going to go through them anymore. You can go through them individually, okay, because we discussed the gist of the topic anyway. Okay, so we move on to life cycle analysis. What is life cycle analysis? It's basically a method for evaluating a product or a system from cradle to grave, from conceptualization of the product to the disposal or the waste management of the product or system. Okay, and it can be used to identify and prevent shifting of impacts from one life cycle stage to another, and this is in line with the idea of sustainability. Okay, and how does life cycle analysis enable this? It has actually four components which enables it to set goals and scope of the study. It compiles the inventory of inputs and outputs of a system or product. It then evaluates based on those inputs and outputs. It evaluates the potential impacts of the product and system. And then, of course, it requires the interpretation of the result of the inventory and the impact and suggestions for improvements for future benefit. Okay, why life cycle assessment? It is actually very much in line with the Sustainable Development Goals, and the most relevant for us here is number 7. But as you already know from systems thinking, these are all interrelated. Okay, so again, why LCA? It is in line with the Sustainable Development Goals, and more, there are obstacles that are faced because of corporate and social pressures, okay, governmental or regulatory barriers, okay, so you have your Clean Air Act, for example, uncertain objectives or goals, and lack of tools to measure the progress of companies or even at the individual level. And in most cases, because it's the relationships are complex, okay, our intuition is not sufficient to use, okay, as a framework for analysis for these kinds of problems, for example, in energy systems. So LCA can provide a systematic method for comparing the products and policies. And these are the 4 components that I was talking about. You have goal, definition and scope, you have inventory analysis, you have impact analysis, and interpretation, okay? So as you can see, the arrows go to and back. So this basically means that the process is iterative, okay? But to make it more concrete in the context of energy systems and for the purposes of this class, okay, these were spelled out actually in VANEC, and the idea of energy consumption over the life cycle is then connected to EROI, okay, as well as energy payback, okay? So let's just go through the typical activities that contribute to energy consumption for each stage of the life cycle of an typical energy system. For example, you have resource extraction. Consumption would relate to machinery used for mining, quarrying, and so on. And then you also have energy consumed in pumping crude oil and gas, etc. Okay, so I'd like you to go through these items. Basically, VANEC and colleagues tried to identify the different activities that contribute to energy consumption with respect to resource extraction, transportation of raw materials. Oh, by the way, they try to make it sequential in terms of establishing an energy system. Okay, so resource extraction, transportation of raw materials, and then you have your conversion of raw materials into semi-finished materials and energy products. You have manufacturing and final production. Okay, so for example, mass production of energy consumption related devices such as steam and gas turbines, wind turbines, etc. Okay, and then you have transportation of the finished goods. Syempre, you have to do that. And then you have commercial overhead for the system, system management. Okay, and then infrastructure construction and maintenance. And you have demolition or disposal of recycling. So it's not just the actual operation of the power plant, for example, no, that requires energy consumption. Okay, there are several stages in the system's life cycle that contribute to demand for energy in order to produce or convert energy. Okay, so that's how we have the idea of energy return on investment. So EROI is basically the sum of energy produced, okay, or converted, sorry, divided by the sum of energy consumption over the life cycle. Okay. Sorry, that is not correct. It's not also known as. Okay. Please disregard that. EROI, so that's one useful concept. And then you have your energy payback time. So this is basically how long can you sort of gain back the amount of energy that you had to spend, okay, in order to create this system that will convert energy. Okay, so energy consumed over life cycle divided by energy production per year. Okay, so these are metrics that you can actually use later on to evaluate how well your system is performing. Okay. Okay, so let's move on to the last part. Okay, and here your answers to the study guide will be useful as we discuss these different concepts: reliable energy source, etc., and then the particular questions that were posted on OVLE. Okay, so any volunteer? Let's first discuss these items here, A to F.